Hooke's law. Not Cookie. Not Captain Hook either. Okay, continue. Yep. I don't like him.
Why? Why? He's handsome.
No, he's the one you supposed to say. Only having the shield.
I don't like him. I don't like Iron Man. I don't like Spider-Man. I don't like the Hulk. I don't like Thor.
He's the bad man.
Deadpool is okay.
Yeah.
And Wolverine. You know Wolverine.
Like favorite movie.
How can I if I have another pen?
Oh yeah, I know. Yeah.
You know Wolverine.
Yeah.
Yes, okay. Exactly. That's it. Yeah. He's okay.
Yeah.
And Deadpool. But the others, no, thank you.
My mom likes.
She likes Wolverine.
Yes.
Very good.
She said he's handsome.
Wolverine is.
Yeah.
Yes. Not Deadpool. Not Deadpool.
Deadpool. It's not coming up in China.
Deadpool's not in China?
They have blood, they have something, talk about the sex, so.
But that makes it interesting.
That's why it's not coming up in
Yeah.
Ah, so
China.
you can watch it,
Yes.
but not your friends.
Yeah.
Ah.
I can take a picture. Ha ha.
Yeah. Lol. Okay. Now, you know, you've seen these before, exercise. No, yeah. So, just to get you thinking, you have the idea that the more you pull it, the harder it becomes, the more force there is, yeah? So as you pull it more and more, you get more and more force. So this is actually the idea for Hooke's law. Hooke's law says, it's a physics law that says that the force, now before you write it down, let me explain something. Now before you write it down, let me explain some of the words. Extend means like this, okay, and compress means like this.
We learned this yesterday.
Where?
In math class.
In math class?
Yeah.
Nice. Alright, so extend or compress by distance x, it's proportional to the distance. So as a formula, the force is equal to minus k multiply x. So a bigger x means a bigger force. So if you pull it a lot, you get more force. Yeah. Why do you think the minus is there?
The distance. The position.
I'll tell you why. If I pull this a lot to the right, which way is this force of the spring?
Oh, left.
To the left. It wants to pull this way. That's why the minus is there.
Pull it to the left.
Huh? Yeah, then your x is minus. Yeah. Okay, k is a constant, and it's about the spring. It's different for each spring. It's also called its stiffness constant. And x is small. We don't usually do a very big x. Okay, so really it's the formula, but if you want to write some of this down.
explain what is
You understand what F is?
force?
The force. So if you had a spring or something, so if I pull this, it wants to pull back, and if I pull this a lot, then the force will be bigger. The x is my distance, I pull it. The F is the force going backwards. That's why the minus is there. If I pull this way, x is positive, F is negative. No?
No.
No.
K again.
K I didn't say about K yet. K is a constant. If the K is really big, it means the spring is really strong and it's very hard to pull it. If the K is small, it means it's easy to pull the spring. Yeah? It's okay? Yeah? Are you sure?
I write that.
Yeah. So big K makes it difficult and a small k makes it easy to pull. Or push if it's a spring. Yes? Continue? Okay. So the natural length, L, of a material is the length at which the material wants to return to. It's the length before any force. That is, it's the length it wants to be at. So for example, look, wait, before you write it down, the natural length is this length. But then, if I push it, its length gets smaller. The natural length is the length when there's no force. It's the length it wants to be.
Is
Yeah?
it possible that the natural length is also the length that is compressed?
No. Because then you squish it out of existence, is it?
I mean, it's like it's really like the maximum. It's like really like coiled up together.
Oh, could the natural length be the maximum?
Yeah. The maximum compressed distance.
No. Natural length, there must be no compression or force. In other words, if it was a spring, you just don't hold it and let it fall out to whatever shape it wants to be. Yeah, so natural length, there you go. Write that down. And you don't have to write that whole box down. You could just write down natural length is the length at which the material tends to return to, if you want. Like, I mean, that's enough too. Yeah? Got that? Yeah? Okay, continue. Amanda? Continue. The extension is the length at which the material is extended beyond its natural length. That is, it's the x. So we call the x the extension.
And what's the compressed?
It's also x.
But negative.
Yeah, that's all. Yeah. Extension? Yeah. The extension is the x. It's how much you pull it. So it's the x distance that you pull it. Does that make sense? Yeah. Continue? Okay. So if you look at this graph, I'll draw a little picture here for you. Where's my... Come on. Yeah. Oh really? What'd you say?
She said she always said.
Chemistry lab, huh?
Yeah.
Yeah. Right, so here's your spring.
Today is Thursday.
Yes, it is. Today is 4 day.
It's a holiday on Monday.
It sure is. I know, trust me, I know this. Right, me too. Right, so here is a spring. Look, come on.
I'm looking at country. I can go home first.
Good for you. Then spring's length is L. Then what I do is I put a weight at the end. So this weight has a force F. And then what happens? It moves down, doesn't it? So this is the X. Yeah? Let's see. Or another way you can do it is maybe you pull it down a distance of X, for example, and there'll be a force going back up of F, or whatever. It doesn't matter. Or, it could be anything. It could be a spring against the wall, and you push it. So if I go back to the graph, I know these are just silly little teacher pictures. You don't need to draw them.
I can draw.
Okay. You see, you think everything I write is great. It's not. Yeah? Now,
Anything that you've done.
okay, fine. Now, if you see here, this graph, when the x is bigger, what happened to the force? It's bigger.
The extension is the x, right?
This is the x, the extension, yeah, and this is the force. So you get a straight line like this. Now, actually, I forgot to say earlier, in the formula F equals minus kx, what's the units for the k?
Meter.
Newton?
Meter.
Newton per meter. Correct.
I guess.
No, it's not a guess, it's clear, yeah.
Okay.
Yeah. Now, please note, listen, often we don't bother to write the minus in because we know that if I pull it down, the force must go up. So often we don't write the minus. Sometimes we do, sometimes we don't. So if you look at this graph, what do you think the slope represents?
Well,
It looks like it's one.
K.
No, not quite one actually. Is it
Okay.
one? Yeah.
okay.
But no, what? It's the K, is it? Let's have a look. So if I have F here and X here, the slope, that would be this part over this part. Would that be the K? If I wrote F equals Kx and this is on the Y and this is on the X, then the K is like the slope. Yeah, so you're right. If you have a graph like this, the slope is the K. So can you draw this graph and then write slope equals K? No problem. It looks like it's about 10. F equals Kx, yes? If I put F here and X here, this is like Y, on the graph. And this is like x. And this one then
So it's a slope.
is like m, the slope. And is there a c? No. There's no c.
But you said the k is minus.
Uh, yeah. So in this graph here, they didn't put in the minus because
But
the-
how can I know?
Now, how can
Yeah,
you
if I draw the
minus
picture,
not minus?
how can you know what?
if they give the example and say you should draw the picture, how do you know it's minus k or k?
Which picture? This
Like
one?
this, yeah.
Ah. For the graphs, we usually don't include the minus because if you did have the minus, then your line would be going like this.
Yeah.
And that's ugly.
No. It's
No.
good. It's beautiful.
As you wish. But in the exam, if they ask you to make a graph like this, they won't want you to put the minus in, they'll want the graph up this way. Yeah.
So when we calculate the questions, we
Yeah.
already should put minus where.
I usually don't put the minus in and just use my picture to know which way the force is going.
So it's always positive.
For our calculations and our examples, yes. But you must draw a picture so you know which way it's going. Yes?
Make it complex.
No, it's not complex.
Because you say, sometimes
It
so
should be
complicated. Sometimes you should negative. Which.
It's like in mechanics, when we have deceleration, because I said deceleration, I don't need to write the minus in my number, do I?
No.
So here, if I say I pull, I don't need the minus because you know pull is backwards. This is what I mean. I don't make it confusing. You make it confusing.
It depends on the question.
Depends on the words.
Or what?
Yeah. Like, if I say I pull to the right, then you know the force goes back to the left. So you don't need to write the minus. You can just write the force to the left. You don't need to say minus.
But even
Ah.
if you say minus, doesn't matter.
Fine.
I know.
Continue.
I know. I just understand.
Congratulations.
And when I'm doing the homework, it becomes,
Then you won't understand. Or you will.
I don't know.
We'll see. Continue? Okay. Continue?
Yes.
Right, so we can see what the slope is. Let's have a look at what the area is. This is F. This is X. What's the units here for F? Newtons. And what's the units for X? Meters. So, what's the unit for the area here on this graph?
Meter, oh no, X multiplied.
Yeah, Newton meter is the unit, right? Does anyone remember what Newton meter is?
Force times distance.
Yeah, but do you remember what force times
Yeah,
distance?
work done.
Yeah, do you remember work is force times distance? That 1 joule is 1 Newton meter.
So the area is the work.
Very good. So the area is the work done on the spring.
It's the area under the ground, right?
Yes. So if you think about it, you can make a new formula, because how big is this base? It's x. And how big is this? F. But what does f equal? Kx. Yeah? So, if I multiply these together, oh, it's a triangle. So the area is half x multiply kx. So you get this formula that the work done is a half kx squared. Yeah. Yes? Yes? Now look, if the keg is very big, what did I say about the spring? It's hard to push. So if you have a very big K and you push the spring, will this number be big or small? Well, this will be big if the K is big. So if I push the spring, X, the K is very big, this is very big, so the work done is very big. But that makes sense. If it's hard to push, it means you do more work when you push it. Yes? No?
Yeah.
Yes? The K is big.
Yes.
It means it's hard to push. If I push it,
Yes.
the K is big, this is big.
Yes.
This is big, so
Work is big.
work is big. But of course the work is big because it's hard to push. We understand? Okay. Continue? Great. Right. So, this is the graph, but in real life, it's not like this. In real life, it's like this. Wait. Maybe you should have gotten that coffee. Why is my graph not straight? What is happening here?
It's getting
Hard.
deformed,
Getting much more hard.
right?
Maybe. Maybe not.
No, that's not. You can push it much more harder.
Yeah, there's a limit, isn't there? So, if you pull it too hard,
It will change the shape.
it changes shape. Now look,
Broken.
it breaks. Look, watch, I'll show you with the spring, okay? So with the spring, if you pull it, it goes like this. So you have force here. Here, do you have more force or less force? You have more, it's pulled more.
You pull.
You pull it, yeah. So here you have more force. But if you pull it enough, it becomes straight. And then if you let go, it doesn't go back to being a spring. Because you pulled it straight. Too much. So then here the F3 now is less. So the graph, what happens is, more X means more force, but then at some point, like here, then you don't get any more force.
It's not zero.
And then it will become zero.
It will
Then
go
when it
down.
breaks.
It will go down back.
I suppose it will go back down to zero then really quickly when it breaks. But in the exam, they just want you to draw it like this. Now, this place here is called the elastic limit. That's as far as you should pull it. Got this? Now, some terms here. So, on the graph, if you look, please. It's straight here at the start, and then what happens later? It becomes a curve. So it goes like this. So this part at the beginning, Amanda,
Okay.
this part at the beginning has a name, and this part here has a name. So this part we call elastic. And this part here, what is the opposite of elastic?
Non-elastic.
No.
Anti-elastic.
No. These are all great guesses.
Hard. Stiff.
Getting closer.
In.
Inelastic.
Elastic. Anti-elastic.
Almost. Not inelastic. Inelastic's a real word, but we don't use it this way. Because it's English, you know.
The
so-
last part plus LESS.
Non-extendable.
Plastic.
Ah.
So you have elastic and you have plastic.
Is that why it's called plastic?
I don't know which came first actually. The material plastic or the use of plastic like this. I have a feeling that the plastic was used to mean it doesn't stretch, and then people called plastic plastic. What's happening?
Nothing happened.
She moved.
No, I didn't.
Continue.
No.
Now I get. Don't worry. I'll put the words up here. So you have elastic. The material follows Hooke's law. Plastic. The material doesn't follow Hooke's law. Elastic limit. The point when it's no longer elastic and becomes plastic.
Wow.
Indeed.
Really, it's just the point.
The point. What are you doing in maths now?
I can't remember.
No, but you remembered yesterday. You said you had the word extend and compress.
The line going where, going move up, move down, and
Transformation.
something across, something like that.
It's
No, it's not transformation.
Yeah,
Just
the
the sign. It's the A something X B plus C theta thing. It's just like how to draw the
oh.
we marked here. Something function.
Transformation of function.
Modulus function. Yes. The one like this.
Yeah.
and more.
And more. Yes, of course. I know. That's my book I made. See my name on it. Got this? Oh.
Yesterday I go to a pet shop, selling hamster. Oh, it's very cute.
You should buy it.
No. I can't see I can be for myself. How can I feed him?
If you can't feed yourself, yes, how can you feed the hamster?
Yes, every time I said to my mom, I want a puppy, and my mom said, I can't, you are enough. I don't want the puppy. But I want a puppy.
Maybe when you go to university, you can have a puppy.
And become bigger, enough puppy anymore.
Yeah. Then you can take it home to China.
Mom, I get a new friend.
Yes. And you can call the puppy Captain America.
No, my friends are Captain America. I just follow.
You can call the puppy Hulk.
Why?
Because it's small at first and then becomes very big. Yes.
But it's not green.
True, not green. Yeah.
Green.
You can put a green clothes on it. Yeah. Okay. We got this now? Amanda?
Yes.
Yeah. Okay.
Simple harmonic motion.
Uh-oh.
You know this?
Yeah,
Yeah.
simple.
I don't want to know.
Now, I used to do the proof, but I will spare you the proof. I won't do the proof. But I want to draw you the situation, okay? So this is actually a common situation in physics where you have a ceiling and there's a spring here and there's a mass here, yes, and the spring is K, and this is moving up and down. So what's the name of this motion? We had this in semester 1. We called it simple harmonic motion. Another example would be on the ground, and you have a spring, and it's also moving up and down. Example would be like in a car. You know the spring in a car under the wheels? Or another example would be like this. And it's moving back and forth like that. Okay. Anyways, for the first two situations, like this or like this, we actually have a formula to calculate the time for one oscillation. Now, last time with the September students, I proved the formula, but I can tell you would be happy not to see the proof. Yeah. So I won't give you the proof of the formula, I'll just give you the formula, okay? Now remember, actually before I just go, remember we had the pendulum, and it's swinging back and forth, and I gave you the formula T equals 2 pi root L over G, and I did give you the proof for this. And the reason I gave you the proof is because I said it's going to be in one of your labs. This is why you need the proof. This one is not in the labs, so you don't need the proof. I'll give you the result. So the result is the time is equal to 2 pi root the m over the k. So just a formula here. The formula and a picture. Formula and picture.
What's the T again?
What's the T?
The either period, right?
The periodic time.
The K is how much?
No, the K is the constant, how strong the spring is. It's the same K as F equals Kx.
M is the mass.
Mm-hmm. Got this formula? Yeah, continue. Now what's very interesting is in this formula there's no A and there's no L. So in fact, you don't care what the amplitude is. It doesn't actually matter. So, I do. I'll draw it with a pencil. The mouse. I can't see, where is it? Oh, there it is. Right. So the A here, if I make the A bigger, so for example, the spring is going like this, but maybe I pull it down more and I let go, so now it goes like this. Does the time change?
Yeah.
No.
Yeah.
No, it doesn't. This is the strange thing. Because if you look at the formula, did I change the M? No. Did I change the spring? No. So if I pull it down more and it goes bigger, same time.
Same time of what?
The time to go up and down.
Oh, I thought you meant like the time.
Now watch, you're getting confused. So imagine I have the spring from the ceiling here, and here's the mass, okay? And I take my hand, and I pull it down, and it goes like this. I get the time. Yeah? Now, again, the same one, but this time, I pull it down more, and it goes like this. Is the time the same, different, bigger, or smaller?
The time.
The time to go up, down, and back up. One, yeah.
Same.
So it's same?
Yeah?
One
cycle, yeah.
down and up, down. Up.
Yeah, sorry, let me show you slow motion, okay? So I pull it down, okay, and the time is the time to go up and then back down to where it was at the start. If I pull it down more and it goes like this, is the time bigger or smaller?
Same.
It's the same, because I didn't change the N and I didn't change the K. So in fact, it doesn't matter how much you pull it down, the time is the same. And this seems wrong. You feel like if I pull it down more, I should have a different time, but I don't. I don't.
I pull it down very fast.
Doesn't matter. Doesn't matter.
How does it break?
But then it does matter. Yeah.
What do you say? The K?
Yeah. It's about the spring. It's how strong the spring is. Continue. Yeah.
Can you say that in a sentence?
What I just said in one sentence.
The time didn't change on.
Okay, hang on. The time depends only on K and M. It does not matter how much you pull it down by. This is what you want. Yeah.
I can make it in one sentence in my language.
Not in English though. Okay. Continue. You want to write this down?
On through my hamburger away.
Why? Hamburgers are nice.
I give it to you.
No, thank you. I don't need your half-eaten hamburger.
I can cut.
Oh, thank you.
I want a fried chicken hamburger, not chicken sandwich or piece
You
of
can
chicken.
make it yourself.
But the fried chicken is not taste good like.
You can make it taste good. You can make it in the kitchen. No? You don't cook? No cooking. Zero cooking.
Yes, because my dad cooks.
Oh, yes. No ability.
Yes.
Okay.
Every time my dad said, you should learn cook. And I said, okay, I understand. And my mom said, why are you here? Study.
Okay. Good, okay. Your father does all the cooking?
Yes,
He's a good cook?
yes. So my mom.
He would make you fried chicken burger?
Yeah, if I want.
If you want.
If I said something is good, my father will try and I will make better.
Good, very nice.
I want a father.
Yeah. Very good. Okay. Now let's have a look. So now we can have a look at some questions. Okay, so here's our first one. Okay, so write this one down. This is our first example then.
What is rubber?
Rubber is, actually maybe we have a rubber band. Does anyone have them?
Rubber.
Oh, you know, it's stretchy.
Yellow. Like orange.
Yeah. Somebody must have one in their pencil case or something.
What is that?
I have
Yellow one.
eraser.
Oh, I know.
Use the tire.
Yeah, that's what I was going to say. The one you put in your hair. It's a circle,
Oh.
and you
Ah.
put it in your hair.
Um,
Yeah.
Why do I have this in my pencil case?
Because you're a girl, and you should have one. I don't know.
I forgot to bring.
Okay. Okay, you got this? Yeah, so let's have a look at this one. Come on. Oh. Gentle. Right, so in our example, what is the natural length? 10 centimeters.
0.1.
And then I pull it, so now its length is 20 centimeters. Yes?
20?
Yeah, because in the question I said, look, twice its length. So, do you see this here? This is the x. How much is the x? X is 10, isn't it? How much is the k? Which is how much? It's in the question.
What?
1. So, how much is the force here? Force equals kx 0.1 newtons. Yeah. Easy? So far. Next now.
How many
So-
questions are there?
How many questions? I got 4. So this is example 2. A spring is hanging from a ceiling and a weight of 2 kilograms is put at the end of the spring and the spring extends by 5 centimeters. What is the constant? Okay, so write that one down. You can write or draw. The spring is from the ceiling, it's 2 kilograms and it makes it extend by 5 centimeters. Okay, can we do this one now? So we want to find the K here. Yeah? Okay, so let's have a look. You have it, Amanda? What is the K? Right. So what you have here, here's the spring, and then you have a weight at the end. How big is this mass? 2 kilograms, yes? So what happens when you put the weight on it? It extends by how much?
X.
Which is how much? 5 centimeters. Can you picture what's happening? Yeah. Now, and it doesn't move. It just you have the spring and you put the weight on it, and it just sinks and then just stays there. You don't move it. Yeah. Right. So, how many forces are on this? How many forces?
1, 2.
Thank you. 2. What are the 2 forces, Grace? There's a force going up from the spring,
And the gravity.
and there's a force going down from gravity. Are they equal or not equal? Equal. What's the force from the spring?
Kx.
Kx. And what's the force from gravity?
G and
Yeah, the weight, which is mg. Yeah. So, therefore, Kx equals mg. So now the K is what we want, equals x over mg, which is 0.05 over 2 times 9.81. Question? It is. You're right. Sorry. Bad morning. Mg over x. Thank you. I was wondering why it was so small. 2 times 9.81 over 0.05. 392 newtons per meter. Yep. Okay, next. A spring is attached to a wall, and a boy pulls it 10 centimeters. How much work was done by the boy? Okay, write this one down. Yep. Yes. Okay. So what you have here, this is the wall, and there's a spring on the wall, and maybe this is a exercise machine. So the K, what did I say the K was?
2.
2. And he extends the spring by what distance? 10 centimeters. So how much work has he done to do this work, this job? it's a half k x squared. Yeah? So let's see.
That's a hot.
Wasn't that the formula
Yes.
earlier? Yeah. So here he did only 10 millijoules. Not much. Yeah. Continue. Okay. Last question. So if you can write this one down.
Every time I bring a big umbrella to go, I'm really happy. Every time.
You should bring a small umbrella down.
And every time I bring my small umbrella to go, ringing very heavy.
This is life. Okay. Got that?
Okay, yes.
Yep. Okay. Yes, I can do it. Okay, so what happens now? Oops. Okay, how much mass do I hang on it? What's 0.1 kg?
G.
What?
Multiply.
Oh, yeah, 0.1 kg is the, yeah. And how much does it extend by? It extends by how much? 5 centimeters? So you know how to find the k. We did that earlier, didn't we? We can say that kx equals mg. So k equals mg over x. So that will be 19.62 newtons per meter.
X is 5, 0.05.
Yeah, 0.05, yeah. Then what happens?
It's let go. Right?
No. Nobody touches it yet. All that happens is you have the. Oh wait. Okay, are we listening? Yeah. So all that happens is you have the spring, okay, and then somebody puts a weight on it gently, and then what happens? It falls down. Then the next part is you take the weight and you pull it down 4 centimeters. So now it's pulled down to here, and then you let go. What happens?
It will go up.
Up, down, and so on. And you pull it down an extra 4 centimeters.
So you say it's,
It doesn't matter.
yeah.
Exactly. I was trying to confuse you. It didn't matter that it was 4 centimeters. You don't care if it was 4 centimeters or 10 centimeters. It doesn't matter. But it just makes it move now. I know I did that to confuse you.
Where? How does not?
Oh, because, you know, I mean.
How long until the weight is...
Yeah, so the question is, how long huh? What? No? Okay. How long until it goes from here to here?
What is there?
From the bottom to the top.
Ah.
Can you see? Yeah? Okay, so what's our formula for t? 2 pi root m over k. So the t equals 0.449 seconds. Is that the answer?
No.
No, why not, Hareen?
Divide by 2, because that's the time it goes up and down.
M is 0.1,
Okay.
19.62. That's not the answer though. The answer is
Half, right?
half of this. And explain why it's half of this, Hareen.
Because the t is the time it takes to go from the lowest point up and then down.
And back down again, yeah. Look for a sec. So you see this t here? That's the time to go from here, up and down. But I only want the time to go from the bottom to the top. So I must take this answer and divide 2. Half the answer. This is the answer I want. Yep. Now, Amanda, you don't need the 4 centimeters to know this time here. You're right. But you do need to know the 4 centimeters if you wanted to know the speed, which they sometimes ask in the exam. So if you make this bigger, will you make the speed bigger or smaller? What do you think?
Bigger.
Bigger, because if you imagine, if you pull it down a lot and let go, it'll go shoot really fast.
Yes.
Yeah. So the 4 does affect the speed, but it doesn't affect the time. Yeah. Okay. Okay. You got it?
No.
Okay. Yes? Can I close this? Yep.